You all now know why Dr. Bengio did not need much of an introduction. Thank you. Let me also introduce Fei-Fei Li from Stanford. She's head of the AI and Vision Lab at Stanford. I know her as the ImageNet lady. And I guess we'll talk a little bit about ImageNet challenges as we go through the discussion. And John Smith is a IBM fellow, long history of research in visual information retrieval, deep learning. And I'm going to be a little selfish. So I'm a trained computer scientist, but I'm not an AI person by training. Lots of other things. So I thought this was a real opportunity to educate me. So I'm going to ask questions that I'm curious about in order to get the discussion started. And the first thing I wanted to ask the three of you is what I would call kind of the hype correction sort of question. Computer science has a kind of a shiny object property that we're all pretty familiar with. And every so often, a group or an individual comes up with a breakthrough. And everybody kind of runs over, and the teeter-totter tips to the side. And so I always worry whenever I see that, it's, oh God, what aren't people working on? So I guess was interesting. Yoshua, when your talk really got to this, it was a discussion about what we know how to do and what we're trying to know how to do. And I guess I'd like to ask the three of you, maybe starting with Fei-Fei, what do we think the limits of deep learning technologies are? What won't we be able to do? Bringing in you weren't here at the beginning, but Tom Sejnowski in the previous session said, don't trust anybody, essentially. So what do you think is sort of beyond this kind of technology?
Okay, so thank you, first of all, for the invitation and great talk, Yoshua. I think already Yoshua mentioned a lot. So first of all, deep learning is a dynamic, changing area of research. Right. So it's very hard to pinpoint what exactly is deep learning. In computer vision, a lot of people who when they talk about refer to deep learning and the success of deep learning is really the specific convolutional neural network model architecture that's under supervised training with big data, meaning ImageNet mostly, that does object recognition. And that is a very narrow definition of deep learning. So when you ask the limitation of deep learning, one way to answer it, there's no limitation if deep learning keeps evolving. That's a little bit of an irresponsible answer, I recognize. And just to be brief, but I also want to echo Yoshua. In my opinion, the quest or the quest towards AI is, especially in my own area of computer vision, it goes from perception to cognition to reasoning, and that whole path we have just begun to get a grasp. We're doing very well with perception thanks to data and these high capacity models, but beyond the basic building blocks of perception, such as speech and object recognition, the next thing is really a slew of cognitive tasks that we're not totally getting our hands on yet. We begin to see question and answering or QA. We begin to see image captioning with grounding. We're just beginning to see these budding areas of research, and down the road, how do we reason? How do we reason in novel situations? How do we learn to learn? How do we incorporate intentions, predictions, emotions? So all those are still not, still on the horizon yet.
So I will repeat what Terry said. Like until we have a mathematical proof, we don't know that something is impossible. That being said, for sure, if you look at the current technology, there are challenges. I don't know if there are impossibilities, but there are clearly challenges. One of the challenges I've worked on for more than 2 decades is the long-term dependencies challenges. So as soon as you start dealing with sequences, there are optimization challenges that make it hard to learn, to train those neural nets to do their job, even or for simple tasks. And we've been studying this problem for 20 years. We've been making incredible progress, but it's still an obstacle. And there are other challenges, like I mentioned some of the challenges that come up in inference in unsupervised learning that seem intractable. But of course, at the same time, we know brains do a pretty good job at these tasks. So there's got to be some approximate methods, and we have already some, that are doing very well on these things. And that's what the research is really about.
John?
Yeah, I think this is a good question to ask. Is there hype? And if there is hype, why is there hype? I think the one thing that's clear is there's a lot of attention being given to deep learning. But to some extent, it is warranted because performance is there. And it's hard to argue against performance. So for many years, my colleagues here, Professor Bengio has worked on neural nets. And it actually took a timing, I think, of many things at once. Fei-Fei's work on ImageNet, sort of coming at the right time with computation, that actually let people realize that there's a class of problems that were previously very difficult, like classifying 1,000 object categories, which were now essentially solvable. So, I think what we're seeing, some of these tasks which we thought were very difficult are now solved. So ImageNet, 1,000 categories is essentially solved. Some other data sets like labeled faces in the wild, which is face recognition, essentially solved. So I think it's hard to argue against that kind of performance, and I think the question for us now is, what else should we do? So it is a shiny object, but there's a lot more out there, at least in the vision sense. I think we know very little about what the world looks like, or how to teach a computer what the world looks like. But I think we're at a very good time now that we have this shiny object and we can think about scaling it to a much larger set of tasks.
Thanks. One of the this is a good segue to something else I wanted to talk about. One of the things that causes me to have one of the most fun jobs on the planet, which is managing a bunch of researchers and developers building out Watson, is bridging out between these, frankly, would you say, constantly changing technologies and sort of the pragmatics of those pesky customers who want to use the system to do things. One of the biggest challenges we have is this whole area we talk about called real-world evidence. And it really is a discussion about reasoning in a particular domain. So if you are going to put a system like Watson in front of an oncologist, and we have, and they're going to ask questions, and they're going to get answers, the first thing they're going to want to know is why. Why did the system, why did the linguistic inference engine decide that this particular passage, phrase, document was a better answer to the question than that one? And I also get this when I ask my team about how much fun it is to debug these things, and Yoshua, your hat on a whatever that was, is maybe a good illustration of some of the challenges of really trying to get underneath how these things work fundamentally. So how about this notion of why as opposed to what these things do? Anybody?
It's interesting you asked this question. It's a very common question. What if we had a human in front of us doing the job? Sometimes the human is able to explain their choice, and sometimes they're not really able to explain their choice. And the way we trust that person is mostly because they do the right thing most of the time, or we have some reason to believe that. So I think there will be progress in our technical abilities to figure out the why. Why is it taking those decisions? But it's always going to be an approximation to the real thing. The real thing is very complicated. You have these millions of computations taking place. The reason why it's taking this decision is hidden in those millions of computations. And it's going to be true essentially of any complex enough system. So the why is going to be an approximation, but still sometimes it can give you the cues that you need to figure it out. But ultimately we can't really have a completely clear picture of why it's doing it. Now, one thing I want to add is I think there's going to be progress in that direction as we advance on the natural language side. As we, for example, think of the example I gave with the images and the sentences. So maybe you can think of the task was not to actually describe the image, but do something with it. But now you can ask the computer about what it sees in the image, even though that was not the task, to get a sense of, you know, why it's getting things wrong, and you can ask where it was seeing these things. So we can design the system so that we can have some answers, and the machine can actually talk back in English about what's going on inside.
And just to add, I think, you know, in most of our research, the interpretability is what you call why, and a lot of us are making effort into that. In addition to the image captioning work that both of our labs have worked on in terms of not only generating the sentence, but grounding back the words into the spatial region where the words make sense. For example, we are recently working on videos and using a lot of the attention-based LSTM models, and there we're looking at how you know, we can actually explain using some of these attention models where actions are taking place in the temporal spatial segment of a long video. So all these attempts are trying to understand the why question, or at least make the model interpretable.
Yeah, I think the question of why is actually a very important one in applications. I think particularly as we look to apply deep learning techniques in industry problems. So I'll give one example. So one of the areas that we're applying deep learning techniques is around melanoma detection. So looking at skin cancer, looking at skin lesion images, and essentially training the computer based on you know, those types of lesions. And what we know is possible, actually it's, you know, the central value proposition of deep learning is that we can learn a representation from those images, from those pixels, that can be very effective for then, you know, building discrimination and so on. So, so we can actually get these systems to be accurate using deep learning techniques. But these representations are not easy for humans to understand. They're actually very different from how clinicians would look at the features of those images. So, you know, around melanoma, around skin lesions in particular, you know, doctors are trained to look at sort of A, B, C, D, E, you know, asymmetry, border, color, diameter, evolution, those kinds of things. And so when our system is making some decisions about these images, it's not conveying that information in A, B, C, D, E. So it's actually can get to perhaps a better result in the end, but it's not something that's easily consumable by that clinician, ultimately, who needs to make the decision. So I think we do have to think about how we're going to design these systems to convey not only final classifications, but a set of information, a set of features, in some cases, that make sense to those humans who need to interpret
So you could just train it to also output ABC.
You can do that, yeah, absolutely, yeah. So, right, so I think there are things that can be done, but the applications may give these requirements, and it may influence how we use deep learning.
Yeah, I think there's going to be kind of a long, interesting discussion as you look at the use of these algorithms in regulated settings, how to characterize them in such a way that the regulators are happy campers, or whatever the technical term is. Let's continue on this discussion around, if you like, domains. one of the things that I've seen about systems like this, the notion of what's an application is a function of who you are. So an application of deep learning, we've talked about image speech, question and answer natural language processing. When you climb up into, if you like, an industrial domain, the things that people who give IBM money understand, banks, governments, insurance companies, now increasingly folks in the healthcare industry. There's really a lot of very, very deep domain knowledge that we have, used to train systems like Watson. And one of the things that's, both a blessing and a curse with deep learning is this, you get taken away from some of the more traditional things like feature engineering that we've all seen. But on the other hand, the feature engineering that you see really embeds deep understanding and knowledge of the domain. So to me, and I'm pretty simple-minded about this stuff, we are going to have to see how these two different worlds come together so that we can mix understanding and knowledge and reasoning at a domain with the kinds of things that we're beginning to see, starting with classification and lifting up on deep learning. So research in this area, what are people?
So first of all, if you have features that you believe are good, there's nothing that prevents you from using them as extra inputs.
Absolutely.
You can use the raw thing, you can use your features, you can use both. That's perfectly fine. You have to sometimes think a bit where you're going to put them in the system, but typically there's nothing that prevents you from using them. Also, researchers working on deep learning have been very creative in ways of incorporating prior knowledge. So in computer vision, Fei-Fei could tell you about the different approaches that people have used. There are lots of things we know about images that we can use essentially to provide more data, more examples, so like transformations of images. And of course, the architectures themselves we're using, like the convolutional nets, they also incorporate prior knowledge. Mm-hmm. And we can play with that. If we have other kinds of knowledge, we can sometimes change the architecture accordingly. And one of the most powerful ways in which we can incorporate prior knowledge is that we have these intermediate representations, and we can pre-assign meaning to some of these representations. You could say, well, okay, so that part of the representation is supposed to capture this aspect of the problem, and that part is supposed to capture this aspect of the problem, and we're going to structure the architecture so that it really takes advantage of this interpretation we're giving. Even though we don't tell it precisely what the output should be for these hidden units, we can wire the network in such a way that it takes advantage of this a priori notion. And there's a lot of work in that and many other creative ways to put in prior knowledge. It's just different from the ways it's been done before.
Absolutely.
But there are many things that can be done to put in prior knowledge. In fact, a lot of the papers in machine learning are about exactly doing that.
Yeah, so I also want to add that, first of all, knowledge, this word knowledge, doesn't come into one level. If you think about Mars' description of the visual system, there's many layers. I think there's a common misperception, and it's a sexy, easy story to tell, but it's kind of misguided, is that a lot of people think before the entrance or the success of deep learning convolutional neural network, the entire field of computer vision is a bunch of us engineering features. And it's true that feature engineering was a big chunk of computer vision research, and that's, some of you might know those famous features called SIFT or HOG. But really, as a field, not only we were looking at features, we were also looking at other forms of knowledge. For example, camera models. To this day, the knowledge about perspective, about transformation are important. And as you look at other aspects of knowledge, there is relationships, there is physical properties of the world, there's interactions, there is materials, there's affordances, and there's a lot of structures. So I agree with Yoshua, a lot of our current research and even past, but with the power of deep learning is to think about how we continue to make models expressive or capable of encoding interesting knowledge structures or acquiring knowledge structures to serve the end task. And one of the things I'm excited about is these blending between more expressive generative model or knowledge-based or relationship-based encoding with the power of deep learning and so on. So it's a really rich research area.
Thank you. John?
Yeah, so I would agree with certainly Yoshua and Fei-Fei. I do think that deep learning has brought some degree of soul searching by computer vision scientists. I think particularly, because feature engineering, actually that was really, that was the chase. That was the race. Until 2012, it was who has the best feature, and SIFT was, getting a huge amount of attention. So I think the field was really hyper-focused on creating the next best feature. But I think now we know with deep learning, the computer can come up with features better than the best computer vision scientists. I mean, and that's even on problems like ImageNet, and yet there are many more, even more complex problems out there that deal with video and motion and dynamic scenes, where I think it's even harder for humans to know what is the right feature, in those situations. So I think there's even more potential here for deep learning to win out in the end. But I think knowledge is actually coming in multiple places. So I think Yoshua talked about sort of transfer learning, types of uses. So when you train from data, those sets of representations are often, they can become knowledge that gets reused, in other applications. So there are lots of examples of learning on ImageNet, then taking those features essentially and going and doing a completely different task, and actually doing very well on that task. So I think there's a lot of knowledge there in these networks that get trained, and that can be stored and shared and reused and so on. And I think there's still a lot of work that has to get imposed from the outside in around the semantic structures. So, we seem to have a very good start on objects and how, they should be organized. There's work happening around places. But there's so many other categories related to people and actions and activities and events, and in domains, food and fashion, and how to organize all of that, I think takes some human effort. But if we do that, then the computer can kind of take over.
Okay, one more question for me, and then we'll open it up to the audience. Two of you, actually, I guess you've all talked about challenges. So, John, with your background in image processing, and Fei, with your work on ImageNet, the same thing. And Yoshua, you talked about the challenge just recently. We doing enough of those?
No.
So throw one out. We got a room.
So I believe that scientific and technical progress has been much slower than it could have been if we had been less obsessed by the short-term objectives. Since I've started my career in research, I've seen this, that in my own work, I've been spending too much time, going for the low-hanging fruits, and the big ideas, that require more thinking and more time, have been sort of paying the price for that. And I think as a community of researchers and people who explore that field, I think we are still way too much into the short-term questions and not enough spending time on understanding. And when we understand something, we get much more powerful. We can build better bridges, better AI, if we understand what we do. Of course, understanding doesn't give you immediate benefits, but it's really an important investment. Of course, you have to do both, right? There's a right balance. But I think especially with what's happening right now in deep learning. People are jumping on it immediately to build products. And that's useful, but we shouldn't forget that the science needs to continue because these challenges are still there.
Yeah, so Fei-Fei, ImageNet has been probably a pretty interesting journey. I mean, if you think back to where you started and where it is now, John says, I think rightly, for 1,000 categories, it's essentially solved. So you're thinking about what next. But do you think this really helped push the state of the art forward quickly? I know it's been kind of entertaining for spectators like me, notwithstanding companies cheating. That's always been interesting to read about. But where's it going?
Right. So I agree with Joshua. I think that there is still a huge place for doing the right challenges. Not for the sake, from standing where we are in academia, not for the sake of immediate products, but really pushing scientific advance to the next stage. I remember in 2007 when my student and I, now a professor at Michigan, Jiaden, and I started with Professor Kylie at Princeton ImageNet, we were asking ourselves the question, why do we want to do this? Is this really just, the bigger the better? Because there was Caltech 101. And I really remembered that we had this conversation and convinced ourselves that we're going to challenge ourselves in the field with a data set of that size that will have to push for new machine learning. That was what our goal is. I even told my student my prediction is the first users, successful users of ImageNet will be coming from machine learning community rather than our own core computer vision community. So following that same kind of hypothesis, I'm putting a lot of thought right now, again, about what my own lab as well as our field can do for the next set of challenges. And there are some really budding, interesting challenges coming up. I really, really like Allen Institute's challenge. That's very NLP oriented about, they're going through the different grades of high school. I think right now it's 8th grade science, 8th grade science exam challenge where you get the Q&A going, the reasoning going. I think we need more of that. In my own lab, probably within a month or two, we'll roll out, I would not call it ImageNet 2.0. We'll roll out a different data set called visual genome data set, which is really going after deeper knowledge structure in the image world, focusing on grounding and relationships. And we hope that the next kind of set of challenges surrounding pictures is about more focusing on relations, affordances, attributes, that kind of challenge rather than categorization. And one more thing probably John can comment on is another area of challenge that I hope some people can take the task of putting together is dynamic scenes. I think there is a huge space to be explored in videos and
Yep.
Either the internet kind of videos as well as videos that's more situational, like robotic videos. So I believe that there's a huge opportunity still for different challenges.
So John, I mean, you and I work for a company where throwing challenges in front of researchers is part of our DNA. So you must think about this a lot.
Absolutely. I think we're talking about two things here. One is evaluations and the other is challenges. I think with evaluations, we've seen that they're absolutely essential for making progress in this area. Everything from what Trek has done in NIST, for information retrieval and language translation and speech transcription and image and video retrieval and so on. These things have been the way to sort of gauge and measure progress, as these technologies develop. So we need those. But yeah, I think we need also, big ideas around grand challenges. I think video is still ripe here. I think we need a lot more progress on that, and certainly I see opportunities to put things together, like question and answering on video and captioning a video and all of this. I think we're starting to see. I think modal multimedia data is actually going to be very important. So, how do we combine the audio and the language and what we see and all of these modalities together with sensors. It could be inertial sensors on a mobile device to give an understanding of the world. And I think where it's all heading is actually just there, which is how can we really completely understand the world? So not just know, what objects may be where, what landmarks, but really what happens where. I mean, just really be able to sort of capture a sense and understand and model, what's going on in our daily lives. So, so lots of challenges. I think the real challenge is getting enough time and people and effort. But
it's not boring. So
yeah.
With that, I'd like to throw it open. I don't know where the microphones are. Where are they? They're coming. In the front here? Jaime, go ahead.
Thank you. Before asking my question, I want to echo one thing you said, that the low-hanging fruit sometimes is the one that's starting to rot. So you should not always be content with just helping yourself to that. My question is, I notice something that I think is a good thing, and my question is whether the three of you agree or disagree and why, is that the original, purity or narrowness, depending upon your point of view of neural nets, is starting to fade, and you're incorporating all kinds of ideas, I think good ideas from other areas. For example, in your image and caption description, you have two different kinds of networks, a convolutional network and another one that's more like a HMM or CRF type structure on the output side. And now you're talking about multimedia, where you have different kinds of inputs, and you also have to treat them in somewhat different ways. So do you think that these somewhat more hybrid approaches that give power also has a drawback in terms of you have to train each part somewhat separately, or do you think that this is a good idea because it reflects maybe the fact that different parts of our brain don't necessarily work in exactly the same way?
So first of all, we can train these things together. They don't have to be trained separately. Second, they're called recurrent nets, and they're very different from CRFs and HMMs. Now, for the bigger question you're asking, of course, it is important to play with these architectures and combine the appropriate types of pieces for the task. If you're dealing with images, you don't necessarily want the same kind of computations as if we're dealing with words. Now, it's all implemented with neurons. It's just that they're wired in different ways, and that in the case of images, we use these translation invariance properties of images that save us training data and training time. And we are adding more components. So I mentioned the memory components. You heard a little bit about it. That's something that's also present in the brain. We have all of these things in the brain, and there are many more things in the brain. As Terry was saying, it's incredibly complex. It has many different kinds of components. At the same time, what's interesting is that for all of these components that we're currently using in deep learning, they all use the same learning principle. And this is probably true to some extent, at least in cortex, that there is sort of one sort of general recipe. If this is a hypothesis, we don't know. And then that's really interesting, because that means we can reuse that principle for many different types of jobs.
Yeah, I don't think I can add. I totally agree with Yoshua. And also, even if you think about the evolution of the brain the evolution is not that pristine, right? Like nature just makes, just patch up parts together in a way. So I think there is some, just some fact of life there that these kind of models, whether it's the biological model here or the actual computer algorithm, grows in a dynamic way.
Yeah, I think this is in part where we're heading with Watson Developer Cloud, which is, to essentially put out all of these individual trainable components that address everything from language to speech to vision to question and answering, and then these become the building blocks for creating potentially much more complex systems and solutions, adapting to industry problems and so on. So I think we definitely see all of these pieces coming together.
Next question. Who's got a microphone? Anybody? Go ahead.
Yeah, so just regarding kind of the specific theoretical challenges that lie in truly understanding these networks, I was wondering if some of those could be expanded upon, as well as what kinds of new mathematics might be required to really solve these problems.
I didn't
Can
quite
you
catch
repeat
that.
the
I
question?
didn't hear everything.
Yeah, so it's basically, to truly understand, we need to have a really kind of foundational mathematical understanding of the networks. What types of new mathematics are required?
Oh, man.
And if you could also
Right.
kind of specifically state some outstanding theoretical challenges.
I think the theoretical understanding of deep learning is really something interesting, and because of the success of deep learning, there are more and more mathematicians, applied math people mostly, getting into this field, and it's great. There's something interesting with neural nets research in general, which is that the theory tends to come after the discoveries. And because they're very complex, and mostly we move forward using our intuitions, and we play with things and they work, and then we start asking why, and maybe a different set of people are able to answer these questions. Right now we're using the same old mathematics, although there are people who are answering some of the questions with aspects of math that I know much less, like the topology and things like that. So there's a lot of potential for understanding, and there's a lot of complex questions that we don't understand. But there's been a lot of progress recently in theory. So we understand a lot better the problem of local minima. We understand a lot better the expressive power of deep nets, and we understand a lot better some of the probabilistic properties of different algorithms. So by far, we haven't answered all the questions, but there's a lot of work and a lot of progress.
So none of you mind being characterized as experimentalists. It's something I've observed too. There's a lot of intuition, and then
Yes.
what's that thing doing exactly?
Yeah, intuition is crucial in this because right now, mathematical analysis is limited in the power that what it can predict. So a lot of it is intuitions and experiments to validate hypotheses. So there's a lot of the scientific sort of cycle of trying to propose hypotheses to explain what we observe, and then testing through experiments rather than proving it mathematically.
And just to add, at Stanford, you see this because first it's the people at CS department making these algorithms, and now there's a lot more interaction between statisticians and the machine learning community here at Stanford. Some of our youngest hires, faculty hires, are actually paying the most attention from the side of statistics department or even applied math, looking at potential theories behind these algorithms. So I predict we'll see more statisticians coming to explain some of what we do here.
Next question. Over here. Okay.
Muradi Ozani from UC San Diego. So neural networks as universal function approximators theoretically have been known for several decades, perhaps even almost half a century by some accounts, and even deep architectures have been explored perhaps even many, many decades ago. And so I guess what I'm trying to say is it seems that the idea of supervised learning theoretically being solved has been well known for a long time, and now thanks to computing powers and lots of data, labeled data, we're seeing these amazing performances, right? But I'm not sure or aware of similar guarantees in the unsupervised learning realm, right? And I think that unsupervised learning is especially powerful in the case of what was talked about earlier, this 90% of dark data. So I guess we don't have that do supervised learning. So is there any theory for the directions we need to go for unsupervised learning?
There is. So first of all, regarding the universal approximation properties, we have similar theorems for a number of unsupervised learning algorithms. So we can prove, so I worked on universal approximation theorems for both machines and DBNs and RBMs. And you can reuse results from the supervised learning framework for other unsupervised learning methods like autoencoders and things like that. So that question is pretty much settled. That being said, there are other theoretical questions to which we don't have answers in unsupervised learning that have to do with these intractabilities that are inherent in solving this problem. So there's a lot more to be done there, for sure.
And just to add to that, there is some evidence from nature that that this might also exist. I mean, the paper by Oshausen and Fields in 1996, unsupervised ICA model for V1 receptive field is kind of a very nice evidence to show that these kind of features and emerges in just unsupervised training of natural statistics of scenes.
Guru, we have time for one more, or are we done? One more, okay, make it good. Last question, in the back.
Beginning, make it good. I don't know if it's a good question. I'm mostly an outsider. I heard a lot of machine learning applications to classification, clustering, and whatnot, but I'm wondering if deep networks are a good match for modeling complex systems. For example, to predict the reading of a sensor in a complex piece of machinery, or to predict the trajectory of something moving in a complex situation. So continuous problems rather than discrete problems.
Hell yes. Anybody? John?
So I could say something about this. There's actually substantial work being done on continuous valued signals, such as handwriting, the trajectories of handwriting, such as acoustic signals, and now there's a lot of work as well in control. So I don't see any fundamental reason why these kinds of applications would be, not feasible. There's lots of evidence that some work may be needed, but I don't see any problem in particular.
Yeah, and we're definitely seeing that also. Looking at objects and their trajectory in video is one example. I think there's a lot of work around manifolds and real value data and so on, where there's applications. So I don't know that there's any fundamental limitation there.
Thank you. So everybody please join me in thanking the panel.